Hi everyone, I'm Kevin. I'm a PhD student in chemical engineering, and I'm making this short video to showcase some of my research progress while using MIT's SuperCloud Compute Cluster. I work in Professor Bill Green's lab, so I work on projects related to chemical kinetics, and today I'll be presenting a project about automated reaction screening by predicting barrier heights using message passing neural networks. So our research group focuses on building kinetic models, and just to briefly explain what that means, a kinetic model contains all of the species and reactions that are important for a given system. Each of those will have thermodynamic and kinetic parameters that we can use to define a system of differential equations that will then numerically integrate to simulate the time evolution of the system. And this framework is really powerful because it lets us explore these systems via simulation, which should be cheaper, faster, and safer in comparison to running experiments. And then with that increased understanding, we can offer guidance regarding how to manipulate these dynamics to obtain a desired outcome. And here we should realize that there's really two open-ended questions. And the first is, how do we know what species and reactions are relevant? And then once we've defined those, how do we know what values to use as the coefficients in our system of equations? And my talk will exclusively focus on this second question. So here's a schematic that outlines the steps for getting barrier heights, partition functions, and ultimately rate coefficients that would go into our kinetic model. And really the point of this slide is just to show that it's a very involved process. There's a lot of steps and it requires a lot of compute resources. And so the question becomes, how can we use modern machine learning techniques to accelerate steps in this workflow? So for example, wouldn't it be convenient if we could just directly predict a barrier height and then skip all of the prior steps? And indeed, that's the project that I'll be presenting today. So the goal of this project is to create a general purpose estimator to quickly identify low barrier reactions produced from an automated enumeration. The model architecture is based on ChemProp, which uses a condensed graph of reaction representation, which I'll describe shortly. And then the input to the model is a 2D representation of the reaction product, and the output is going to be the estimation of the reaction's barrier height. So the model starts by transforming the reaction and product into an attributed graph. So atoms become nodes, bonds become edges, and example initial featurizations are shown here in the top right. We then combine the reactant and product to create a condensed graph of reaction, which just represents a pseudo transition state structure that is then passed to a graph network, which iteratively updates the atom and bond representations. And details about the message passing framework can be found in our paper, but the point is that we get these updated atomic vectors, which are combined into a reaction embedding, which is then used to predict the barrier height of interest. And now that I've very quickly gone through the methods, I'd like to present the results. So qualitatively, we see that we have very good results, and that's because the predictions fall along this parity line for the entire range of barrier heights from 0 all the way up to 150 kcals per mole. So accuracy is maintained across all of this diverse chemistry. And when looking at the histogram, the errors are centered at 0, which is exactly what we want to see. And then quantitatively, our model had 75% fewer parameters than other published models that were trained on this same data set. So ours is lightweight and thus more practical to integrate into prediction workflows where we want to quickly estimate barriers. Also, our test mean absolute error was 2.57 kcals per mole relative to this very highly accurate level of theory. And just to put that number in context, it means that our model is giving predictions that are better than a good DFT calculation, which would have a 3.5 kcal per mole error relative to the couple cluster value. So that's really exciting, and it should offer huge time savings for the user. And with that, I'd like to thank my advisor, Professor Green, as well as my thesis committee members. I also want to thank Lucky, a former PhD student in the group. It was a pleasure collaborating with you and working on this barrier predictor project. And I also want to give a very special thank you to the SuperCloud team. So during my PhD, I've had the opportunity to work on a lot of different projects, and that includes projects to create kinetic mechanisms. I've also contributed to software engineering projects that make it easier to create and refine these kinetic mechanisms. And then I also created my own kinetics dataset, which was used to train the model that was discussed today. And then finally, I've worked on several machine learning projects whose goal is to accelerate steps in that traditionally tedious workflow that I showed earlier. So the point that I want to make on this slide is just that every single project benefited from the resources that SuperCloud offers. So I'm really happy that MIT supports this because SuperCloud has been an essential resource for both my education and productivity as a graduate student. The compute power, I think, really lets us explore research questions that would not be possible at other universities. So with that, I conclude my talk, and thank you for listening.